Hello, everybody, and welcome to the last hardcore talk in this year's Joker conference. It's actually my favorite talk for this year, and with a great speaker, Andrew Dinn. So Andrew is working.
I'll have to live up to that now. Thanks, Bob.
Yeah, it's not easy to find information about Andrew on the internet, but I can tell you that he's working on OpenJDK, on Hotspot, on Java for many years. I think he joined Red Hat about 15 years ago. He worked on many different topics. He worked on Bytemain, which is a bytecode instrumentation framework. He worked on GraalVM. He was one of the main authors of the ARM port of Hotspot. He is a distinguished engineer at Red Hat. He also worked on JEPS 352, which is the non-volatile map byte buffers. So a lot of different topics. And he's like a real expert and hardcore hotspot engineer. Today he will talk about static Java and the relationship between Graal native image, Project Leyden, which we are still waiting for official incantation. So, Andrew, the stage is yours. Please go on with your talk.
Okay, well, with an introduction like that, I have to confess that rather than being an expert at anything, I'm a jack of all trades because I've actually done all sorts of other bizarre things. We can maybe talk about that later, including working on list machines and graphics drivers and all sorts of stuff. So I know a little bit about a lot of things, but hopefully I know enough about this topic to actually give you some useful input and to sort of put it into context anyway. That's the plan with this talk. So I'm ready when you are, Volker. Are we ready to go ahead? Okay, so let's start. So the talk today is about static Java, and the intention is to really try and give some definition to what static Java is, and that's a theme that will come out again and again through the talk. Obviously, GraalVM Native is a specific implementation of a static Java app deployment model, but it's one way of doing things, and there are certain choices. Some of those choices have different results, different consequences. I'll bring in OpenJDK project Leyden because the point of that project is to bring some definition to what static Java is or should be, providing an extension to the specification of static Java, and also a reference implementation and TCK potentially to actually normalize things and make sure that whether you deploy on a dynamic VM, the normal VM, or a static Java application, you get essentially the same behavior modulo places where maybe there's some room for change. So let's begin by just talking first about what static Java means. It's not a determinate thing, actually, what that's supposed to say. It's clearly a deployment model for Java that's a new way of doing things. You can take all the bytecode, all the class files that define an application, all the classes and the class files that provide the JDK runtime functionality, the functionality that's provided by the JVM, and you can obviously, one way or another, it's possible to build that into a single self-contained executable that does the job of the Java application and deliver it with just that one program. So there's no need for you to deploy any class files onto the target host or pull class files off the network. And also you can get rid of some of the things that are in a conventional Java runtime, like the interpreter, the JIT compiler. Probably some of the data that's used to manage this code base that's being loaded can be thrown away because you don't need to keep track of as much information. And that's seen as a container-friendly model for Java. It gives you, certainly with GraalVM, you get smaller footprint for a lot of applications and faster startup. You don't necessarily get as fast performance, although it can be fast. It depends upon what you're doing. So that's actually not an automatic result. There's no guarantee that just by packaging something up as a self-contained executable, you will get those results. It's a question of how it's implemented. And one of the consequences of moving towards the static build time, a static model where you define various things at build time, is that some of the things that Java is capable of doing at runtime, the dynamic aspects of the language, are not really possible to support, or certainly not if you want to have these goals of small footprint, fast startup. Obviously, you can implement a program that does anything, with the appropriate technology. But the reality is that when you make a static deployment, you're going to not be able to do it for certain types of programs or not support it in an efficient way. And that's really what's interesting. what needs to be changed in the static deployment world from the dynamic world, which things will work, which things won't work. Is it just a question of JDK functionality being slightly different or being not being available? Is it JVM functionality? Do we need to make changes to the Java language? And that's really where the Leyden project is interested. At what level do we actually allow for differences, and how can we keep Java essentially the same, whichever deployment model you choose, at least for some recognizable and understood subset of applications using certain types of JDK behaviors. So I've mentioned Java being a dynamic language. What does that actually mean? In what ways is Java dynamic? Well, obviously, the most important thing is that the code base evolves during execution. You load classes at runtime, and so the program actually develops and determines, possibly under application logic, which code is actually called. Now, you could say, well, there's a whole universe of code, and there's a subset of it which the program will ever load. But actually, that's not quite true either, because the program can actually generate classes on the fly. And given sufficiently complicated application logic, those classes can be generated to do anything. It's a Turing-complete language, and bytecode is Turing-complete. So, it's not even a closed universe. There's actually a mechanism in the JDK for loading services, which basically loads a class and a load of auxiliary classes to implement a block of functionality. That's used in the JDK, and you can replace things like the locale service provider, the security provider, there's various other provider APIs in the JDK runtime, as well as in middleware and in applications. So this is really baked into the language in quite a big way, and you can replace standard functionality even in the JDK. So it's not clear that you have a definite target for any given program, and the application can make it more or less ambiguous as to what's going to run, and it can only be decided at runtime what will happen. To just underline how complicated that could be, classes can actually define their own class loaders, and they can delegate according to their own delegation patterns to do loading of classes, and class loaders can come and go, and so can their classes. So it's not just that there's not a fixed code base of classes or a type space of classes. Also, the class loader relationships between those classes can be under the control of of application logic. So it's really quite a complicated picture. And similarly with modules, modules control visibility of packages and within classes and across modules, within modules and across modules. The module layer, the basic module layer, gives you stuff from the module path, but you can build your own module layers and then regulate class visibility across layers. So it's really quite a complicated space, the actual code space we're talking about here. And then the execution model supports this evolving code model and evolving type model. You have reflection and you have methods and var handles. So if you can load a class by, let's say, whose name is computed, you don't know you can't refer to methods and fields of that class by name. There are indirect method mechanisms for identifying what behaviors the class supports. And then there are ways of invoking those behaviors or accessing fields indirectly. Reflection in the older JVMs, JDKs, methods and var handles more recently. Similarly, so with a class loader, being able to indirectly load, you've got basically indirect structure linking the whole program, indirect linkage, as well as the direct name reference linkage for classes and their behaviors and state. But the program state itself also evolves as well. It's not just the type system and the code that's available. There's actually the ability to extend what's essentially a global space of static state every time you load a class. It can have static fields, and those are initialized, and they have to be they add to the state space before anything tries to use them in interpreting code or executing code, compiled code. And this happens repeatedly, so the state space of the program is being continually expanded. It's very interesting, just an aside to point out here, that static init is done before any interpretation or compilation happens. So at any point we're going to compile a method, you know what the actual current type space and state space is, and you can it's all kind of, so things are at known locations. You know where the metadata is and the actual field values are. So you can actually compile stuff in as constants. You can use direct linkage when you do compiling, as well as profiting from profile information. So you can build a very tightly linked program that's very efficient, even though you've got this evolving space. And it's quite complicated the way that initialization can happen. Static initialization can recursively embed this same pattern. During initialization of a class, you can load other classes that can involve compiling code for those classes if they're complicated enough. So the order in which this state space evolves is actually quite flexible. Depending on where the application goes, you may load different classes in a different order, and they may recursively load things. And that means you have to break cycles even in static init. But the compilation process still copes with this because it actually knows at any point it's compiling what the current state is and compiles accordingly. There's also a need sometimes to recompile, because if you load something, it may be that you've made assumptions not just about the current type system, the current space state, the current code, but actually assumptions about what might turn up later. Like you might say, this interface only has one implementation, let's just call it direct. So the de-optimization model, another dynamic feature, allows recompilation to make sure that compilation decisions are revised. So the compiler keeps this very efficient code model executing while at the same time having this evolving code and type and space and code model underneath. The compiler can actually execute it very efficiently. The VM itself also responds dynamically to the runtime environment. There's various parameters of the runtime, like which garbage collector you're using, which JITs, whether to use compressed loops, whether to use things like vector units or encryption units on the hardware. These can all be configured on the command line, but of course they have to be available at runtime. You have to get the configuration right when you start up. If you don't configure anything, the JVM just adapts accordingly. And because it's compiling late, it gets the ability to make sure that the code actually is responding to the runtime environment and doing the right thing according to what's best with what's available on the hardware. So again, it's a dynamic aspect of the runtime that it is capable of responding to where it's being run. All the tools that are in that go along with Java that are used with this runtime, they rely on dynamic capabilities of the runtime. Agents rely on the ability to transform code at runtime, to have the code installed and maybe have methods de-optimized, and then they can uninstall things and go back to the original code, and it gets recompiled again. The debugger relies upon interacting with the interpreter, so it needs to de-optimize code in order to be able to debug. You never debug compiled code. The flight recorder, if it sees an event in user code, a new JFR event, it will generate event handlers, and it will bytecode transform places where events are actually triggered to either include the event message creation or disable it at the bytecode level so that you can switch it on or off and have no overhead when it's not being used. And JMX and JCommand, they normally just talk to the JVM and the JDK and report state, but they can execute reflective operations to update state. So all the environment, all the tooling is also relying on this dynamic nature. So now we've got this very, very flexible runtime where things are happening under application control. How can we do all this up front and decide how to do all this up front and make it static? The answer is, if you want to do that and do it in a way it's efficient, you can't always do it. You can do a lot of the work, though, and you can get a lot of programs to work in the same way as the dynamic VM. So the first thing you need to do is be able to identify all the code you need ahead of time, because you've got to compile it in. You're not going to be able to compile at runtime. That's relatively straightforward for all the named reference or the direct references. You can just analyze the bytecode from an application main class and identify all the classes, all the methods, all the fields, and there you go. You can build up the direct linkage structure very straightforwardly. The really important bit here is not to include the kitchen sink. To do that efficiently, you really need to actually have some way of making sure you just get only the classes you need. And you can do things like abstract interpretation of the bytecode to identify things that may or may not actually happen at runtime and maybe restrict things. And that's the thing that GraalVM tries to do. But there's all the indirect linkage. And in some cases, if you've got a method that's a reflective method or a reflective field, you might know where that's going to come from. And you can make sure the relevant target method code is compiled in. But in some cases, you might compute the name of the method you want, or even the class that you're going to load it from. So that has to be configured in order to make that complete. It's not possible always to derive that at compile time, at build time. And similarly with service implementations, you can't always know which service is going to be loaded because the name of the service implementation class that you want to load might not be able to be identified in advance. So again, you need to somehow have a user intervention. The same actually applies with class path resources. Those can be loaded from the jars. Well, they're not there if you're going to use this static deployment model. So you need to make sure they're already linked into the runtime before you start. Now, one of the things that make this difficult, as I was saying before, you're trying to do this for the world of the target runtime, but you're doing it at build time. And so you can't really execute the application code in all cases or initialize application state to identify what would happen because you're doing it in the wrong world. And the target runtime might have some differences in the operating system environment, the hardware, just the way things actually run, which you can't emulate. To what degree can we do that? Well, there are certainly some cases where we can't emulate what's going to happen. Imagine an application defines its own class loaders. You can't really necessarily create them in the build time environment and use them to emulate the class loading dependencies that would happen in the application because they can only really do that loading job in many cases in a running application. It might depend on application state. So there's a limit to how you can implement certain capabilities of the program and actually emulate them at build time to work out what would happen at runtime and build up the same situation in the pre-compiled program. You really need to do this at runtime. There's actually a converse problem. If you want all the classes to be in place in the runtime in advance, and you've got an application class loader that's expecting to be able to define classes on the fly, well, then that's not going to work. So sometimes you can't use class loaders either at build time or at runtime. So some programs just aren't going to work. So are you just stuck with the class path and the module path? Well, no, there are certain cases you can deal with, like you could cope with a fat jar and know how to load things from that. You could deal with war loaders or ear loaders that are used in a lot of middleware code. That's fine. But there's a limit to what you can actually manage to actually make work here. And then there are issues which may also affect things like service loading that is to do with environmental things. So, for example, if you initialize all the locale provider service on the basis of the build time environment, you might be able to actually make sure you've got the right locale provider for the ENUS locale that you're building in. But if you want to run that in a Chinese locale, you won't actually have all the right code for the Chinese locale service provider or whatever language it is. So you can't necessarily, unless you know in advance what some of the runtime configuration is going to be, you can't make sure that the right code is available. There's another issue also with taking away the loading. If you don't do class loading, there's no clear point at which you would run your static initialization. So when do we run class static init? What do we do about that? Well, the obvious thing to do, step one, is to try and emulate the dynamic JVM. We try and run the initialization at points where a load would have happened if we'd been running on the dynamic JVM. That's a bit woolly sort of thing anyway. And also what makes that hard is you need to do all the initialization for all those classes that the bootstrap of the JVM does before the application starts running, because that should have state that's there and that's initialized in the particular order before the application does anything, because the application might modify that state if you do it later on. Then it's clear when you get to the application at what point the application might trigger a static init. If it tries to create a new instance of a class or it accesses a static field or a static method, at that point, the class should have been initialized. If you mention foo.class and that gets it executed, evaluated as part of execution, or you call class for name or class loader load class or find class, at that point, the class should be initted. So at the micro level, we know where things need to be done. But you could get to lots of places that you need to do that, and you need to initialize once. So you're going to have to check all through the execution, and you're going to have to use a lock because threads might race to try and do this. So actually, that could be quite expensive. And obviously, if you do a careful analysis, you would know that if you've already created an object of a given type that's a parameter to a method, then you don't need to initialize the class when you call a static field. Access the static field of that class in a method. So there are cases where you can remove this, but you need to actually do quite a lot of analysis to get that right. Could we get rid of all this overhead of doing the static init during execution and all the locking by doing some of it up front? Well, yes, that's true, but then you've got to make sure you do it in the order that the program would expect to do it, because the ordering might make a difference to the outcome. And actually, you can't necessarily do it all up front because the application itself might do things that change the outcome. Imagine the application always initializes class A before class B, but between doing that in one path, it might also update the state of class A. In that case, if you move the initialization of class B forward, you would initialize and get different state. Is that legitimate? It's not going to replicate the same behavior as on the dynamic VM. So you could maybe do this some of the time to avoid some of the costs, but you need a hybrid. You'd need a very careful analysis to make sure that's safe. Okay, what about the third option? This is really, sounds a very exciting option. Doing it all at build time and getting it all out of the way. It's certainly better for performance. The problem is you're doing this as it would happen in the target environment. So you've got all the problems of working out what would happen that we've mentioned before. So all the above considerations, so you're not sure exactly what's going to happen. But you've also got to be a bit clairvoyant. You've got to know what's actually going to be the target environment, because things about what happens in that target environment could actually mean that things you compute in the build time are not going to be valid values for things that are computed at runtime, because you might be building in stuff that depends on the build time operating system or JVM, and they're not appropriate for where you're running, or the build time hardware. And actually, you can't do build time initialization from all or everything anyway. Only certain things can be done. And actually, we'll find also, if you try doing this, you have to cheat. And I'll give some examples of that and show you how Graal does that. So build time init is generally fine. If you've got a final primitive constant field and it's initialized to 257, it doesn't matter when it's initialized to 257, it's always going to have the same value. So, it doesn't matter when you do that, and you can do that safely at build time. If you've got a field that's initialized to a string, it's always going to be that string that's the initial value, and you can just create that whenever you want, as long as it's there before you try and use that field, or before any code is in danger of updating it. Even mutable objects, if you create an object that has zero, a complex that has 0 and 0 in it, it doesn't matter that you might update that complex object. It's always going to be initialized with the real imaginary part of 0. So you can create that any time. It's always going to create with the same values. So it's not these aspects that matter that actually stop you using built-in initialization. And actually, if you can do built-in initialization, there's a real motivation to do this, because imagine, for example, you've got a field that's a static field, and you work out that actually, although it's a non-final field, the code that you're going to compile into the application is never going to call something that updates this field. It's effectively final. So if that's a constant value, when you're coming to compile things at build time, if you already know what the value is, you can fold that into the compilation. If it was possible for it to change, you'd have to have a load of the field and then use it as a parameter of the computation. Now, folding constants into the compile process means you can do an enormous amount of optimization. Maybe whole paths through the method just disappear because something's always true, not false, for example. So this is a really valuable optimization opportunity. But unfortunately, there are just certain types of values where you really don't want to do this. It would actually cause real problems if you build something into something. It's got to be done at runtime. For example, if you've got a static field that holds a thread, in some application creates a thread object, that thread points to a pthread. A file stream would point to a local open file handle. You can't just create that, stick it in the image and the image heap, and then have it as a sort of pre-initialized object, because it's not connected to the relevant pthread or the relevant file handle when you start up in the runtime. There's other values where it's not the value itself, but the semantics of the value that make a difference. You can create a random with a seed in it, and you can just create that in advance and have it in your image when you start up, but you've always got the same seed for your random, and that's not going to give you the right random behavior. You might create a hash in a credentials object, which is computed by running some code. If you don't run that at runtime, you always get the same hash. So you really want to do that at runtime, not at build time. If you compute values by calling out to a native method in a library, or if you, for example, pull some value out of the JVM or out of the operating system environment, it may not be appropriate to use that when you've got a different instantiation of the library in your target machine, a different JVM or a different operating system environment. So you can't really trust those values. And clearly, if that's the case, you can't trust values that are derived from any of these sorts of cases, because they may also be tainted, and then it may be that you really need to compute a value at runtime that would end up being different. So it matters how values are computed, and it also matters how they're consumed. Here's a few examples just to show. There's a class called unsafe constants. This thing I actually wrote, and it has a page size field, which is used by a class unsafe. It's initialized to 0 statically because the JVM bootstrap injects the actual operating system page size. Now, if the compiler were to actually link that into the runtime and use it in the runtime and fold it into actual code, the methods of byte buffer would actually be using the page size of the build time host, and they actually refer to this value. And you would want it to use the value of the runtime host. So you really want that field to be something that's loaded after init on the target host and used as a parameter to the code rather than a constant in the code. The same thing with the locales I mentioned before. What the default locale is, the setting of that environment variable in the operating system drives the initialization of the text processing system. So if you initialize on the basis you're in the ENUS locale, if you're running with a Chinese locale, you'll have the wrong setting for your default locale. So you really need to pre-configure that rather than just build it in at build time. And the local file system provider, which is used to create an object of which identifies the local file system, that file system object caches the local root and working directory. And actually, that's a problem because that's the local root and working directory of the build time host using whatever the user DR was in that build time system. That directory may not even exist on the runtime host. There's a similar problem with JVM configuration. You need to know the JVM configuration up front, as I mentioned before. So things like which garbage collector, whether you're using compressed oops, whether you want a vector unit, that affects the way you build the code. And you've got to make decisions about this at build time. So you've got to get that right for whatever the target host is. And if you try and run your static application on the wrong host, it better check this and make sure it's actually you're trying to use the right values for those things. Otherwise, you're going to get a problem because the code won't play ball. And then the same with tools. It's really difficult to deal with the tools issue. A lot of the tools just don't work because they're so heavily predicated on having a dynamic VM. With agents, maybe if the agent just does some one-off static transformation of a class, well, you could do that at build time and then have the changes you want. But often agents make changes and undo them, or they install state in the runtime that the injected code refers to, like Byteman does. That just won't work. JFR does this. It creates event handlers in the actual runtime, and then it bytecode transforms to call them or not. Well, with Graal, it was modified so that it creates those event handlers at build time, and they're always there. And then it was modified to use a runtime on-off switch, as well as also changing the JFR implementation. The actual transformation bit needed changing. So this has been finessed in the work we did on JFR, but it's not. It took a lot of rewriting. For other things, we had to do complete replacements. With Graal, we couldn't use JDWP because there's no interpreter, so I just basically built dwarf debugging for support. Of course, that means you're debugging optimized compiled code rather than interpreted code, but that's all we can do. And it's useful, but it's not really quite as good an experience. Nobody's yet dealt with the other JMX and JCommand. Something will come up for that for monitoring, but there probably won't be the ability to update the environment because that would require code to update arbitrary bits of the space, of the state space, and that's just not going to be available. Okay, I started talking about GraalVM Native. Let's go into it in more detail and see how does GraalVM fit into this world of static Java. It does a very, very good closure analysis. It can drive the full reference closure, and it's also able to prune that closure very aggressively using a good understanding of what the application is going to do. As well as throwing out code, it'll throw out state that's not needed, including fields and instances that are not actually used. It supports class loading by redefining the class loaders so that when a class loader is asked to load a class, it hands back the class that's already been loaded and is already pre-created, or it throws a class not found exception. So it works, but it doesn't work with the standard class loaders. And modules are also supported just as recently. So if you put things on the module path at build time, you can actually query the module relations between the system modules and those other modules and identify what's exported and what's opened. But there's no module layering because there's not really a lot of use for that, or either say nothing dynamically because you can't add classes dynamically because you can't add modules dynamically. Reflection works, and Graal is very good at inferring what are the targets for methods and fields, but it needs to fall back to user configuration in cases where it's ambiguous. Method handles similarly, and also chains must end at a direct handle. You can usually work out which method a direct handle is targeting, but sometimes it needs configuration. But that's enough to make lambdas work because it's clear with a lambda what the target class is for the lambda, what the target method is. Service and resource loading is inferred wherever possible, and again, doesn't need to fall back to user configuration. GraalVM Native has special case some of the JDK service provision. Locale support is possible for you to configure the default locale that the system's going to target to, so you can get the right locale, but you specified at build time. If you want to do any other locale-specific processing using other locales, you've got to specify them at build time so the relevant locale information can be compiled in at build time, ready for use at runtime. And this default file system issue where you've got a file system object already created, I'll go into this in more detail. It's actually created at build time because without a default file system, you can't build time initialize a whole load of the file subsystem, and therefore you can't initialize applications at build time in applications like Netty that use the file system. So you need to create one of these, and that means you've got the wrong information, and the JDK code has to be patched to fix that, which is a bit hacky. We'll see if that works in a bit. There's a real imperative to do build time init for the JDK. Almost all of it is. There's occasionally a few things that are runtime initted, but it's really important for performance. There's actually a few cases where JDK classes are build time initted and runtime initted. I'll explain an example of that. It sounds a bit questionable, and it is, but it can work. Applications can also be configured to do build time initialization, and this is actually something that almost all the frameworks try to do. And so Graal, to make sure this is safe, has a quite a powerful analysis to check this. It checks for things that must be runtime initialized, like the things I mentioned. It also checks for derived values, and it rejects built-time initialization if you push it too far. Now, the reason that all the frameworks try and do this is it's absolutely critical to the small JDK footprint and the fast startup. And in fact, we see for applications too, and for middleware. If you think about it, when you build all the state at build time that's used to compute state that the application uses, a lot of that state that you build is actually just footsteps along the way to get to the stuff the application needs. And you don't really need that in the image. So you can throw that stuff away. You can squeeze it out of the image, a whole lot of static values that were just auxiliaries, and you can throw away the types associated with them. So that's quite a big reduction in what you need to squeeze into the image. And actually the code that was used for computing those intermediate values, because you've run out of build time, you don't need it in the runtime environment. So a lot of initialization code can be got rid of, and you don't need to run that at build time either. So a lot of time is saved. And that's really important for the locale processing. That's one of the things that makes the JVM take a lot of the startup time. And if you get rid of that, actually you save a lot of startup execution. The other thing is, of course, that this same thing unfolds in middleware and in application code. And because there's a sort of hierarchy of dependencies, the more you build time init in the JDK, the more you can build time init things in middleware, the more you can build time init things in application code. So getting these savings really requires you to do it as much as possible. And anything that you can't build time init will have a sort of pyramid of things that depend on it that mean you do more things at runtime. So let's move on to an example of reinitialization. Here's a class, a JDK initialization feature that's one of the Graal classes that manages the process of doing the build time initialization and checking it. So things like Java IO and Java lang packages, they're all initialized at build time. There's a class called epoll, and that's initialized both at build time and at runtime. And the excuse is that it calls it epoll event size. Let's look at the code and see what that actually means. Here's the snippet of init code, and there's various constants that are operations that are passed in to do polling control operations in the operating system for file descriptor polling. And so they're all final constants, and you really want to just have them as constants that you fold into the compiled code. So you want them to be built time initted. But there's unfortunately this field called size of epoll event. That's how big an FD vector for a set of file descriptors is. It's limited by the number of file descriptors an open process can have. So that has to be computed by calling into native code. So you don't want to fold that into the compiled code at build time because you may have a different value at runtime. So we need to initialize this class at runtime to get that field, but we need to initialize it at build time to get the other fields. And we need the compiler to be smart enough to use the fields that are valid and not use the fields that ought to be loaded as a runtime parameter from static state, rather than as a compile time constant. And of course, Graal does that, but it's a little iffy. It works. Now, build time init is obviously very desirable, but it's occasionally desirable and wrong. And the case I mentioned before is an example of that. The file system instance that Java base requires to initialize Java base, you need to create a local file system. In class file systems, there's this static field called default file system. It's a Unix file system, and A Unix file system has in it a reference to a Unix file system provider, so you also need to create the provider at build time. And it has a default directory and a root directory that the constructor sets up from the user.dir property of the environment it's running. So we've got the build time paths here. The problem is these are private fields, so there isn't even any JDK code that can update them. They're just one-off. So how do you get around this? You build this object at build time, things refer to it, they're going to try and use this, only it's not going to be using the right values. Well, let's come to Graal substitutions. Graal has this fantastically complicated and very powerful mechanism for replacing classes at runtime, globally rewriting JDK code or any other Java code that comes into an application. And it can rewrite it, in this case, to something equivalent, and it's used to fix this problem. It's really there because this model with the whole of annotations for transforming classes is used to take the underpinnings of the JDK runtime, where it sits over the OpenJDK JVM, and transform those API classes so that they sit over the substrate API that the substrate Java and Java virtual machine provides. So to make that transplant work, you've got to do major surgery. It's like a sort of Frankenstein. You take a different VM and you plug it under the JDK, and there you've got Frankenstein's head on the body, and it's a different body. It's a very powerful mechanism. It's brilliant, and it works, but it's an absolute sledgehammer to crack this nut that we've got an invalidly initialized object. And it's very, very much the wrong thing to use because it's doing radical surgery. I'll show you an example with this example and work it through to show what sort of thing happens. Here's the class in the Graal system that replaces Unix file system. It's called target Unix file system. And it retains one of the fields, the provider field, although the type of that field is also substituted. So the field type changes and the field object will be an object that's translated as well. But that field is kept as is, an alias, and we've still got that as initialized. The two fields that have the wrong paths in are virtualized. This class Unix file system accessors is used to provide getters and setters that will be called wherever a get field or a set field happened on default directory or on root directory. So it's got getter and setter methods that are identified by name, and that means the bytecode will be universally replaced, not just to replace the type, to replace these fields. The field values computed in the build time initialization will be thrown away. And these are virtualized and replaced with injected fields that store the same type of value, but note the difference. They're now packaged public, they're not private. And in the so they're now packaged private, not private. There's also another field. These are going to be initialized in the runtime at first use. So we need to do that with possibly a race. So we need to inject an extra field, a flag field that tracks whether these have been initialized or not. And also, when we come to recreate this object in the runtime, what we want is to have the object that's already there, have its state reinitialized in exactly the same way it was at build time using the standard initializer. So we grab the bytecodes from the init method and we're going to bind them to a pretend method, a native method. It's not really a native method, called original constructor that takes a provider and the user TR string. And we're going to actually rerun the initialization method to reconstruct this object in place. So it's a bit of a hack, but it does the right thing. It actually updates the object and recreates it with exactly the same logic as the original, but using the runtime directory. Okay, so that's fine. What do the accessors do on this auxiliary class, Unix file system accessors? The setter, just when it's asked to set, say, default directory, it will actually set the injected field. So we're sidestepping the data to the new field. What about the getter? Well, the getter reads the field we've sidestepped the data to, but before it does it, it sees whether this is the first call or not. Have we been reinitialized? If not, it calls a reinitialize method. And what the reinitialize method does is when we get in, it's synchronized. It checks that we've actually were the first thing to get there, that no other thread has tried this, and it calls that original constructor method, which it can do because it's a public package private method, so it's got access to it, to run the init constructor the way it was run before, but this time using the runtime user property. And then we set the flag we're initialized, and we've now got the object back in the state it should have been, and we've repaired the fact that it was actually build time initialized wrong. So this is a mechanism for getting things to work right when we've set something that's wrong. It's an inherently risky thing to do. It's very easy to unwittingly introduce bugs, and particularly security bugs we're really concerned about. And it's very easy to introduce subtle disparities between the static and dynamic behavior and start to put a wedge between what happens at runtime and what happens at build, what happens in a runtime system and what happens in a build time compiled system. Obviously, this is something that we would like to get rid of, but we've got a problem that in some cases, maybe we could just redefine the JDK runtime code to fix this and make different Java code changes. And maybe the same thing can be done in application code. Maybe there's a need for language changes, like having some privileged static reinit paths that will be called when reinit is appropriate that could fix this. So that you can still keep the sort of existing code, but have a different initialization model. But we've got the problem of legacy. The JDK and middleware and applications are all using this mechanism to fix things that they want to build some in it for efficiency, but aren't necessarily going to do the right thing because they've got build time state when they need runtime state. And even if we got this into newer versions of Java, how can we backport this and get this back into 17 or even worse, JDK 11? How can we get the middleware and the application libraries updated? It's like the pig in the snake problem. You start with the base library layers and it takes forever to get all of the libraries you need for a given application to be updated. So this is something we're going to have to live with for quite a while. Maybe we could tame it and make it a bit more safe, and that might be the best thing to do. Right, I'm going to talk a little bit about, just summarize where Graal gets its performance benefits from, and we'll see there's a few other things I haven't talked about, and then we'll go on to talk about Leyden. So we've seen the footprint and startup, minimizing the image code is one of the things that gives a smaller footprint. We're able to drop methods that we know aren't called. And remember, that means if a method gets inlined into another method, you don't actually have to have a separate compiled version of that method. It can be dropped as long as it only exists in line or it's never called. So there's quite a lot of opportunity for getting rid of methods. The same thing with all the build time init static code. We can drop a whole lot of that. We can minimize the metadata by dropping all the unreferenced types that aren't used by the application, aren't used by the initialization. GraalVM does a clever trick of taking the Java lang reflect class object and actually putting all the what would be normally JVM state in the dynamic VM into that Java object because it's a Java in Java VM. It has a substitution class called dynamic hub, and that has very little need to work as a reflective object. It's just a proxy for the reflective object because reflections all being compiled in. Without needing to do any dynamic runtime execution to make it work. So it actually just has most of the state that you need from the class object that's in the JDK, the JVM, the K with the class with a K, the size of the object, where the oops sit in an instance, vtables and so on, but a minimal subset, and it stands as a proxy for reflection, and they've merged into one object. So you get quite a reduction in the metadata for that. You hardly need any information about the methods and fields in most classes. In the case where a class is going to be used for reflection, you might need to know what to return for the get declared methods, get declared fields calls, but you don't normally need that for most classes. And you may need to know about offsets and things and have some compiled code for reflective operations or for handle operations. But again, that's only a very small part of the code base where those operations happen. So the metadata is really quite reduced. The image state itself, we can see you can drop a whole lot of static fields that are just there as stepping stones for what the application needs. But imagine you've got several static fields that are read-only. They just hold a string. It might be 6 different state fields that hold foobar, and at some point the application is going to read that. Well, it doesn't matter where you get that from. You can actually deduplicate them to a single global constant, and all the code that wants to use that static field can just read that constant. So, and the same with numeric primitive fields. You can just deduplicate them. So a lot of the state space of read-only stuff collapses down to just one single copy. And then if you're lucky enough to have an instance field that's not used, imagine you've got a library which has an object which has various bits of state in it, but the paths that are used only use some of that state. You can even make your objects shorter. And that's really beneficial because you get per object savings. And then Graal also managed to minimize linkage. I talked about the JVM having the ability to compile things very tightly. Well, you know where all the code's going to be, so direct Java to Java calls can use a fixed offset or a direct address. Foreign library calls, you can use symbol linkage to get a direct address when the image is finally linked. So you've got very tight, no indirection in the actual invocation. This is a problem that the AOT project in OpenJDK had. It could only have indirect access. And similarly, all the linkage of code to metadata and data and, for example, class pointers in an object header, these are all at known locations. All the initial heap objects are pinned. All the constant values are pinned, classes, the fields. So all of this can be linked directly very efficiently. So you get all that tight linkage and efficient access with no indirection, just like you had in the OpenJDK runtime. And what this means is that when you load the Graal image, there's no need for a lot of linkage to be resolved at load link time. This is already in place when the image is built at image build time. So there's no mapping and copying of data, no updating of pointers by adding offsets, which can take quite a lot of time at startup. So that's Graal. That's how it manages to do what it does, and well, some of the details of how it does what it does and how it gets the benefits it does. So let's talk a bit about Project Leyden now. Now, Leyden is here to try and sort of take Graal as it is, take OpenJDK and Java as it is, and somehow normalize this and work out which things are actually allowed and which things aren't. So one of the deliverables is extensions to the Java specifications, possibly the language spec, the virtual machine, and the runtime, JDK runtime, Java doc specification, to say what things could be different in a static deployment, which things don't have to work or allowed to fail in specific ways that are actually acceptable. And that's probably the biggest and most important task. The second task is then to extend the Java TCK to actually also deal with that situation and actually validate that any implementation that can pass the TCK and therefore is spec compliant. And the third thing is also possibly, this is something we've considered, and we don't know whether this is how far this is going to go ahead, a reference implementation of static Java built on top of OpenJDK technology so that the project can have its own validation of whether static Java implementation is correct or not, and can actually validate the specification and make sure it's possible to implement the specification. And how far we go with that and how far we try to get something that's optimized is really up for grabs still. So I'm going to talk a bit about what we've been doing on the Leyden reference implementation. We've been doing experiments just to fuel an understanding of this and see where we can go with a reference implementation and how far we can push it towards something that actually deals with some of these issues of trading off performance against functionality. So the idea we've been looking at is that we would reuse most of the hotspot TM in a target runtime, and we would build the components that were derived from the application code and link them into a hotspot JVM library. So we'd keep a lot of the core runtime. We wouldn't have stuff to do with the optimization and all the governance that supports making that sort of things work, but we'd have the stuff that does callouts to do all the standard stuff. We wouldn't need the runtime stuff that does link resolution of classes either, but there's a lot of the runtime support that would still be retained. We need pretty much all the GC code. We'd need the memory management system that sits underneath the GC code. That's going to have to be supplemented slightly because we'll need to generate an initial heap, and the GC will have to be able to take a heap that's at a fixed mapped address in the program and make it part of the full range of heap space. It includes dynamically allocated heap memory, and it would have to know that that data is pinned. But we could generate. We're basically using the same stuff for managing virtual memory. We'd need to generate the class metadata from the application, but in the same format that Hotspot would expect all the class state to be in, so that it can just be linked into the JVM with as little hand linking at runtime as possible. And we would generate a code cache in the format that is laid out in Hotspot, and also link that in to the JVM. And then we wouldn't need to have any of the code for the interpreter or the compilers, the class splitting code, the bytecode parsing code. So a whole lot of code could be thrown out of this actual implementation. And so we would have a generated ELF library that would be contain all these three generated sections I mentioned, all in which would map to fixed addresses in the final image, linked to a static version of the JVM, and we'd have as much runtime build time linking as possible. So the sections we generate are the code cache containing all the compiled code. That should be pretty much look much like it does in the runtime. The metadata section would have all the class information. It would have the symbol tables and dictionaries, the loader graph that identifies the class loader relationships between all the classes. We wouldn't need to have things that are relevant to linkage or to compilation. So the constant pool cache, for example, which is the interpreter's link resolver scratchpad, the method data object that keeps track of de-optimization information and speculative compilation information. We could cut some of that out of the metadata model, but it would mostly be the same model. And then we'd also build an initial heap region, which would look like just a bit of Java heap with Java objects in the expected Java format. They'd all be pinned objects, so they couldn't be relocated by the garbage collector. And the GC would have to know how to sort of have a bit of predefined heap and also then extend it with dynamically allocated heap. But it's just a region, and there's already some support in this in the GC for CDS to use. So we've done some experiments towards just implementing some of the parts of this. The first experiment we looked at was a reduced VM experiment. Can we build libjvm without this code in? And that involved if-defing a load of stuff out and just making sure we could build a library. But we also wanted to test it by, we worked out we could import the built library into a parent VM as a dynamic library. If we, because we removed all the initialization code, because you wouldn't have anything to generate all the classes and all the heap data and whatever, we had to do some cross-linking to provide it with stuff it needed. But the idea was to run this and actually test it and make sure you could bootstrap the VM we built and do basic bootstrap, assuming a lot of the data was the data that wasn't generated, that was going to be generated by there, was borrowed from another VM. The next experiment was to do try and do a sort of closed world analysis. The idea here would be to use the CI interfaces that are used as an abstraction barrier between the bytecode parsing layer and the class loader and the compilers. Rather than have to do everything at the level of bytecode, we'd have the class model of these CI interfaces provide CI classes, CI methods, and so on. And that's the model that the compiler consumes. So if you do an analysis at that level, you can also end up with a class base you can feed into compilation. And it's also plastic. If you've got a class that represents some particular class in the input base, if you decide that you want a class that doesn't have certain methods, you could provide a wrapper class which only presents a subset. So it's a good level at which to do it. And this really requires rewriting C2 to allow a CI method to be expanded to a class, a compiler graph, and from that you can identify the references that it makes to other CI classes, CI methods, or possibly even an inline method graph. We have that's actually a lot more work. So we just tried to do some of the initial work using a bytecode analysis. One of the things that's really important there, when C2 builds a class graph, it does its best to throw away bytecode and build a partial graph. So you need to actually have C2 not de-optimize, not plan to de-optimize code and really build a full graph here. And that's something we had to do also for some of the other experiments. Another experiment was to try and generate an ELF code cache using C2 as a compiler. So we generate a lot of compile methods, rather like AOT. We actually generated the methods you'd expect in memory, but worked out how to lay them out in the sort of format the AOT would provide. Again, we had to make sure we built full methods. We didn't put de-optimization paths in. Speculation wasn't such a problem because we had a list of all the classes that we needed and all the methods we needed to compile things, so we could avoid speculative compilation actually became determinate and decisions could be made. Another thing C2 doesn't do is it doesn't resolve calls at call time. It resolves them later. So we had to sort of force through some of the resolution to make sure that when we compiled all the methods, all the cross method call linkage was established. So that's another part of the test that was done. And ideally what you get is an ELF library with a code cache and various other fields in, which are the implementation of various static fields referenced in the JVM. We managed to get that to work. Two other experiments that we haven't yet done, and these are quite large experiments and there's a lot of work to do, was to do something similar for the metadata section. And this could be based to a large degree on the CDS code, but instead of generating the classes in memory format with some relocation that's done by CDS, we would actually do it all with automatic relocation via ELF and do it to a greater degree. So CDS doesn't necessarily put every class into the CDS class segment that writes out to file. We wouldn't be able to miss out stuff because you need the whole shebang. Also, CDS writes the classes and some of the basic indexing information. We'd really want the whole class-loaded data graph, all of the metadata model written out, everything. And then also, with this really, to do it completely, needs also to have the initial heap data and the code cache and cross-linkage as well as internal linkage using ELF relocation. So you really need this and the initial heap experiment to get all the 3 bits in place. The code cache you can do because you can hand crank stuff, but doing this really requires everything. And if you would do this, then ideally, most of the JVM link would just be resolving static fields with symbols that identify stuff in the metadata section, plus a bit of fiddling with the memory regions to import things into the right part of the memory space. Another experiment was initial heap generation, similar to this, but generating a heap data section with one area for read-only stuff and one area for read-write stuff. This would then also have its own internal linkage established using ELF, and also objects would link to their class pointer by having an ELF relocation into the code cache, into the metadata section for the relevant class. This would need the GC to be able to accept this at startup and build it in as an actual heap region as part of the heap address space. And by doing it this way, we could avoid the copy and link relocation that CDS has to do. It will be in a known location, but you could actually have it automatically without having to do any runtime initialization. So these different experiments would mean you could get a fully linked program with everything pretty much ready to link at build time. And we think all the pieces are in place. It's just a question of doing all the work to build all these. It doesn't look like it's infeasible. So to summarize where we've got to, our reduced VM attempt, we managed to get a library without some components. The only problem there was we had to make changes all the way across the code base to exclude things. If you don't want the interpreter, you'll find that you need to change the frame code, which is runtime code, because there are methods that are specific to interpreted frames. There are methods that mention end methods, and actually you only want compile methods, so you have to get stuff that's specific to the in-memory representation of the dynamic VM and replace it with generic stuff that could be could be pre-generated stuff. The code cache experiment worked. We saved it and reloaded it as an ELF-lib and managed to execute code up to all the bootstrap code up to Java minus version. So we proved that that's possible, although we had to obviously hand link the metadata and object data references in the code to existing stuff that we'd already pre-initialized, rather than have it be in part of the saved library. Work started on the CI closure analysis. A lot of that has been theoretical work that Dan Heiding has been doing on the working out the full closure and working out the static init ordering, but he's actually started doing work on using the CI wrappers to provide a way of populating a full class closure. And of course, we haven't yet started on the metadata initial heap. Right, well, I've only got a few minutes left, so maybe we'll just have to have some questions in the session afterwards. But anyway, that's the summary of where we've got to with Leyden. I hope that's explained a bit about where we're going with static Java and made it clearer what the problems are. And I'll be very happy to talk about any of the things that you want to clarify further in the session that comes to follow. Unless there's room for maybe just one quick question here. We've got a couple of minutes, 2.5 minutes.
Thanks, Andrew. That was a very interesting talk.
Bit of a whirlwind.
I have one question here in the talk until in the chat until now. So I will just read it from Artyom. If I understand correctly, what happens with file system on build time is that there is a special part of code created which is then reinitialized and uses a proper file system while running as a native application. So
yeah, that's right. Yeah. And that means that you basically run different code to the JDK code. And of course, it so happens that it does the right thing. We've made sure of that. The Graal team have made sure of that. I mean, I've checked it as well. I mean, that was the thing I was very interested in making sure it worked. And it's really important to get that to be right. But that same thing is happening in application code. Things in the applications and things in middleware are being replaced with something which is equivalent in theory. And people who write that code are doing it, but it's very easy to get it wrong, or it's very easy to get little nuances where you open up a security hole. Just as a little prize, that code I showed you, there's actually a thing the compiler cheats to get to work as a bonus for anybody who can spot why it is that substitution model there manages to do something that really shouldn't be able to do. So it's fine, it does work, and it's because the Graal compiler allows something that maybe shouldn't be allowed, but it knows in this case it's safe. So even in something that looks really nice and bulletproof, there are actually nuances as to why it works that are subtle, and actually because this substitution mechanism is just doing surgery and you're putting bits together and not necessarily getting what you expect because of you've got to really know what you're doing. So that's really the issue we have with the substitutions. And it would be nice if we had something that had a few more guarantees and was a little more user-friendly, and we could actually do it in a way that is much more, can really show that you're doing an equivalent thing rather than just allow you to hack code that ends up being the same, because you then got to understand that yourself.
Okay, so I think we're running out of time here. I invite everybody to join the Zoom chat. I think everybody got a link who listened to this talk. So bye-bye here, and see you in the Zoom chat.
Thanks very much. Bye, everyone.
Bye.